Is reality made of mathematics? Here is something strange that physicists rarely talk about. When we probe the deepest structure of reality, we do not find things. We find equations. Particles are not tiny billiard balls, they are excitations in mathematical fields. Forces are not pushes and pulls, they are symmetries in abstract spaces. The more precisely we describe nature, the more it dissolves into pure mathematics. This raises an unsettling question. Is mathematics just a tool we invented to describe reality? Or is reality itself made of mathematics? Physicist Max Tegmark has proposed the most radical answer. The universe does not merely have mathematical properties, it is a mathematical structure, nothing more, nothing less. Physical existence and mathematical existence are the same thing. Welcome back to the Conscious Observer. Today we ask whether numbers are more real than atoms. In 1960, physicist Eugene Wigner wrote a famous essay titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He marveled at how mathematical structures, developed purely for their internal beauty, repeatedly turn out to describe physical reality with uncanny precision. Complex numbers, invented centuries ago as abstract curiosities, are essential to quantum mechanics. Non-Euclidean geometry, explored as a mathematical game, became the language of Einstein's spacetime. Group theory, the study of abstract symmetries, predicts the existence of particles before they are discovered. Why should the universe obey mathematics at all? Why should equations dreamed up by humans in their studies match the behavior of quarks and galaxies? Wigner called this a miracle we neither understand nor deserve. Perhaps the answer is that mathematics does not describe reality from outside. Perhaps mathematics is reality viewed from within. Mathematicians have long debated whether their subject is discovered or invented. When you prove a theorem, are you uncovering something that was always true or creating something new? Platonists believe mathematical objects exist independently of human minds. The number pi, the prime numbers, the Mandelbrot set, these would exist even if no one ever thought of them. We discover mathematics like explorers mapping a continent that was always there. Formalists disagree, viewing mathematics as a game of symbols, meaningful only through the rules we define. There is no mathematical reality beyond human notation. The Platonist view gains support from the unreasonable effectiveness Wigner described. If mathematics were merely invented, why would the universe care? But if mathematical structures exist independently and the universe is one of them, the mystery dissolves. The universe obeys mathematics because the universe is mathematics. Max Tegmark's mathematical universe hypothesis takes Platonism to its logical extreme. He proposes that every consistent mathematical structure exists physically. Our universe is one such structure, the one whose properties match what we observe. But there are infinitely many others, equally real, corresponding to every possible set of axioms and equations. Most of these mathematical universes would be simple, sterile, devoid of anything interesting. Some would have physics utterly unlike ours. A few would support complexity, life, consciousness. We find ourselves in one of those because we could not find ourselves anywhere else. This is a kind of ultimate multiverse where existence is granted to anything mathematically coherent. There is no distinction between physical and mathematical reality. To exist mathematically is to exist physically. The universe is not described by mathematics. The universe is mathematics. This forces us to ask what we mean by physical existence. We usually think of physical things as having substance, being made of stuff. But modern physics has progressively emptied matter of substance. Atoms are mostly empty space. Particles are excitations and fields. Fields are mathematical entities defined at every point in space. What remains when you strip away the mathematics? Tegmark argues, nothing. There is no non-mathematical residue that makes something physical rather than merely mathematical. The feeling that physical things have an extra something, a realness beyond structure, is an illusion generated by our evolved brains. We perceive solidity in substance because it was useful for survival, not because it reflects fundamental reality. At the bottom, there is only pattern, relation, structure. There is only math. If reality is purely mathematical, what about consciousness? Can equations feel? Can structures experience? This is perhaps the deepest challenge to the mathematical universe hypothesis. We know from the inside that awareness exists. Pain hurts. Joy delights. Redness is vivid. How can abstract mathematics generate subjective experience? Tegmark suggests that consciousness is what certain mathematical structures feel like from the inside. Just as a wave function describes a particle from outside, but a particle does not experience being described, so too we are mathematical structures that happen to include self-referential complexity sufficient for awareness. The mathematics is the same whether viewed externally or internally, but internal viewing comes with experience. This is not a solution to the hard problem of consciousness, but it reframes it. The question becomes, which mathematical structures are conscious and why? If the universe is mathematical, is it also computable? Can its evolution be simulated by an algorithm? This is not guaranteed. There are mathematical structures that cannot be computed, problems that no algorithm can solve, numbers that no procedure can generate. Kurt Gödel showed that any consistent mathematical system rich enough to include arithmetic contains true statements that cannot be proven within the system. Alan Turing showed that some questions cannot be answered by any computer in finite time. If the universe is a non-computable mathematical structure, it would be fundamentally beyond simulation. This might explain why consciousness feels irreducible, why qualia cannot be captured by functional description, or it might suggest that our universe happens to be one of the computable structures and our sense of irreducibility is an illusion. The relationship between mathematics, computation, and physics remains one of the deepest open questions. Physicists often use beauty as a guide. Equations that are elegant, symmetric, and simple tend to be true. Why should aesthetic criteria predict physical reality? If the universe is a mathematical structure, perhaps we should expect it to be beautiful. Consistent mathematical structures tend to have elegance because elegance often correlates with deep consistency. Ugly, arbitrary structures are more likely to harbor contradictions or complexities that preclude existence. Evolution may have also tuned our mathematical intuitions to resonate with the structure of reality. We find beautiful what reflects the patterns in which we are embedded. The unreasonable effectiveness of mathematics might extend to the unreasonable effectiveness of beauty. When a physicist says an equation is too beautiful to be wrong, they might be detecting genuine features of mathematical existence, not merely projecting human preference onto nature. The mathematical universe hypothesis connects to another theme from our series, the primacy of information. If reality is mathematical, and mathematics is ultimately about relationships and structure, then information is more fundamental than matter or energy. The physicist John Wheeler proposed it from bit, suggesting every physical quantity derives from information theoretic origins. The holographic principle, which we explored earlier, encodes three-dimensional physics in two-dimensional data. Quantum mechanics can be formulated entirely in terms of information processing. Perhaps mathematics, information, and physics are three perspectives on the same underlying reality. The universe computes itself into existence, each moment arising from the logical implications of its structure. We are not things in a world, we are patterns in the great computation, thoughts in the mind of mathematics. We began by asking whether reality is made of mathematics. We have seen that physics increasingly supports this view, that matter dissolves into equations, that mathematical structures may be all that fundamentally exists. If this is true, we are equations that have become aware of themselves. We are theorems that can feel. We are proofs that ask what they are proving. This is either deeply alienating or profoundly connecting, depending on how you hold it. To be mathematical is to be part of an eternal, necessary structure, something that could not be otherwise, something true in every possible sense. You are not an accident, you are a consequence, an implication, a truth written in the language of existence. In our next episode, we explore what lies beneath the apparent solidity of space, the quantum vacuum, where nothing turns out to be everything. Until then, remember, if you are made of math, then you are as real as 2 plus 2 equals 4. Keep observant.